Hey, Earth Science. We're still talking about the air as our unit, and part of that is the weather, and I can't think of a better way to talk about the weather than actually being out in it. Not only that, but I mean, it's Earth Science. It's about time I brought the Earth along. However, I regret to say that I'm going to have to blow the Earth up now. This could take a minute. Okay, there we go. Come over here. So, hold on. Come here. So, I'm also outside with my kids because it was either. Okay, I just wanted them to see that. You can say hi. Say hi to my class.
Hi.
Hi. Okay, you girls go play. Go play. So it was either Daddy says.
We're making friends with animals.
All right, thank you. It was either Daddy says, no, I have to stay inside and work, or it was we all go outside. So we all went outside. Anyway, let's get on to our Earth Science-y bit thing that we are here to do. We're talking about air and the Earth and air on the Earth, the atmosphere. We've talked about how sunlight is more direct. What is this weird pose? More direct in the equatorial regions, but if you're up on the pole, from that point of view, it's always at an angle, which means it's less direct. So that means that the heat is more intense at the equator, and that this causes air to typically heat up and then rise, and then it'll move north. Now, I oversimplified this earlier, and I want to make sure that I sketch it out in a diagram a bit better, because we had a couple degrees of latitude with some details that we needed to pay attention to. So one of them was obviously the equator. That would be at 0 degrees latitude. Next one up was at 30 degrees latitude. Now, obviously, we don't live all over the Earth. We're going to connect things better if we're just talking about the place where we live. So I'm going to talk about things mostly in terms of the Northern Hemisphere, specifically North America. I mean, that also kind of translates to Europe, some that we're on opposite sides of the Atlantic. But none of us are really very familiar with Southern Hemisphere geography. But for all intents and purposes, everything up here happens down there just in reverse. Okay, so we've got warm air around 0 degrees latitude, around the equator, that rises up and causes a band of cloudiness and precipitation. Okay, so think of it like, you know how the bathroom gets after you take a shower? It's just like that all the time around here. Because there's all this warm air rising, full of moisture, usually from the ocean. So that's where all the rainforests are. Most of the rainforests are around this latitude. So we're talking about the Amazon River. Okay, we're talking about this central southern Africa. That's where India would be. That's also where Southeast Asia and Borneo, Sumatra, Philippines, Indonesia are. Even just around Central America. That is, I'm actually not sure if I was holding that high enough up for you to see. All of the regions here, or at least most of the Earth's rainforests, are around there. Okay, so that air rises and then it tends to cool and sink around 30 degrees latitude. And if you remember, that is where the horse latitudes are. Now, because that warm air from the rainforest regions has cooled and sank, it's also now dry. And you'll find that this is where so many of the deserts in the northern hemisphere are.
What I found.
Oh, you should throw that away, honey.
What? It's going to be perfect for a machine that we're going to make.
All right, then have fun. So if you look at like 30 degrees latitude, you're right in the Sahara Desert, or the Arabian Desert, the Gobi Desert. Let's see, where are we around here? The Mojave Desert. So a lot of the northern hemisphere deserts are at that 30 degrees horse latitude because they're getting the cool, I shouldn't say cool, it's the dry from having cooled air that is returning from rising from the rainforest. So the region around here, the tropics, is basically governed by that air exchange. And that's why being so close to the equator, you're not really going to have seasons in the tropics. The way that we have summer, fall, winter, and spring, that doesn't really occur in the tropics. What they have is a dry season and a wet season. And that just has to do with how they move in and out of that high intensity sunlight. Anyway, let's keep going with these winds. So we talked about the prevailing easterlies and the prevailing westerlies. So let me just make a mark on here in the Atlantic where we can see it. The winds between, actually the Pacific, it'll be easier to see. Between 0 and 30 degrees latitude, we have mostly prevailing easterlies, which means that the winds are blowing from the east. Up here, though, we have mostly prevailing westerlies, which means the winds are blowing from the west. And so this is going to be the kind of wind pattern that we would be used to. So as I'm looking up at the sky, I'm facing kind of like northeast right now, and all my clouds are going like that across the sky. Obviously you can't see that because you'd be looking at the sky and not me, but you've got a sky. Go look at your sky. Sure, it's the same sky, I know. Okay, so we talked about westerlies and easterlies. So the interaction of air from different parts of the world at different temperatures with different water contents is what's going to cause weather. So yeah, global wind patterns, that does matter, but that's kind of like the backdrop. So let's talk some specifics. Let's talk about clouds, shall we? In fact, why don't you take a look at some clouds here? I'll point you up. There's some nice, pretty clouds. See? Yeah, pretty clouds. Okay. Oh, my glasses just fell off. Hey, honey, could you pick up my glasses? Thank you. Yeah, that was not a smart move, Mr. Estes. Okay, so hopefully you enjoyed those clouds. All right. Just in case you needed proof that I was outside. So let's talk about clouds, what they are, how they form, all that lovely stuff. So first of all, what are clouds made of? So clouds are made of water. They are made of condensed water, and depending on their height, they could also be ice crystals. But the point is, they're made of H2O. Now, last I checked, H2O is heavier than air. So how does it get up there? Well, we need to talk about what makes things float in the first place, and it is a force called buoyancy. Buoyancy is the upward force in a fluid exerted on an object that causes less dense objects to float. So warm air is buoyant, that is, it floats, but only when it's surrounded by cold air. So it's like a context thing. So it rises until its density matches surrounding air. So you're going to end up with, if you've got two different temperatures of air in the same area, the warm air will tend to rise, and it's because it's expanded, it's less dense, which means that there is what's called a buoyant force. In other words, the air pressure of cold air tends to almost like squeeze the warm air upwards. All right, so as the warm air is going up, right, and when it goes up, then there's this thing called the dew point. So you're familiar with the condensation of water, hopefully, either from physical science or from experience, where water in a vapor state can change to a liquid state when it comes into contact with something cold, right? So, so you're going to end up with warm, wet air, or I shouldn't say wet, it's humid, rising to a point where all of a sudden the temperature is low enough to cause condensation of water. Warm air is actually going to cool down about 10 degrees Celsius or like 18 degrees Fahrenheit for every 1,000 meters that it rises. Sorry, I'm just making sure my kids are okay. There's like a bear over there or something. I don't know. All right, so once air rises to the point where it can cool down to the dew point, that would be the temperature at which water will condense, that's when the clouds form. That height is called the condensation level. So you may have noticed when you're looking at a whole bunch of clouds, they're all at the same height and they all have fairly flat bottoms. That's the reason why. It's because there actually is a certain height at which the temperature is low enough for condensation to occur and for a cloud to form. So there's a couple different ways that the air can end up going up to do that. First, as I mentioned, is just convection. That is heated air rising, being replaced by cooler air underneath. There's something called an orographic uplift. That's the lifting of air over a barrier, such as a mountain range. In other words, air is like moving across a landscape and then it encounters a mountain and it has to move up to go over it. So that's another way for air to move up. It can also be lifted along weather fronts. We're going to talk about fronts in more detail. But for now, a front is a boundary between two air masses with different temperatures. Okay, so clouds are made of water. Now, those water droplets or ice crystals, depending on the height, are microscopic. They're much smaller than a typical raindrop. It's actually only about 1% the diameter. And see, diameter, length times width times height. If you do 1% cubed, you end up with 1/millionth. So it's actually 1/millionth the volume. It would take 1 million cloud particles to make one raindrop. So they're so small that they can stay suspended in the air. Even though water is heavier than air, they are so small that they start to become on the order of the molecules in the air. Obviously, they're not the single molecules of water, but they're small enough to be held up, kind of like you'll see dust floating. It's the same thing. Okay, so in order for an actual droplet to form and it not just be water vapor, you need what's called a condensation nucleus. That would be a small solid particle such as a speck of dust, smoke, or salt that is suspended in the atmosphere. Even aerial bacteria, like microorganisms floating in the air, can become a condensation nucleus. Because of the extreme conditions there not being hardly any water at all, it may even remain liquid at sub-freezing temperatures, even down to 40 degrees below Fahrenheit. What is this, honey? All right, so let's talk about the types of clouds. This one's actually kind of nice because whenever you see a cloud now, hopefully you'll think, oh, that's you'll think of its name. So there's a couple different roots for names. Anytime you see cirro, C-I-R-R-O, that refers to high clouds. So cirro. Then we've got middle clouds, which are called alto. If you sing, maybe even your voice part is an alto. Those are middle. Then we've got strato, which are low clouds. Cirro, alto, strato. Those describe their heights. Okay, now let's talk about their appearance. We've got cirrus, which describes wispy clouds. It comes from a word that means like a lock of curly hair. So cirrus basically means curly and wispy. Cumulus describes lumpy or puffy clouds, and that is from a word that means accumulate. It's the same root, accumulate, cumulus. And then stratus describes clouds that form a sheet or a layer. It's related to like the word for strata of rock, like stratus. It's a word for layer. So almost think like a sheet cake. Okay, so let's talk about the train. Let's talk about specific names of kinds of clouds. Probably going to get one more train whistle here. Maybe another. Doom, 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 doom. I just love the trains around here. That's a 13th chord, by the way, if you're curious. Anyway, so let's talk about specific names of kinds of high clouds. The high up clouds, these cirro clouds, they are composed mainly of ice crystals because the temperatures are so low up there. So we already mentioned cirrus as thin, wispy clouds. They're generally present in fair, pleasant weather. Hey, kind of like I have today. Now, building on the root of cirro, if you take cumulus, meaning lumpy or puffy, and stick it onto cirro, meaning high, make it a cirrocumulus cloud, that would be a small, high, puffy cloud. These could be as like individual clouds or in long rows. Stratus, meaning like the layer. So cirrostratus would be high up layer. Cirrostratus, those are thin clouds that often cover the entire sky. Sometimes they can be so thin that they're difficult to see. So like the only sign that they're even there might be like a halo around the sun or moon. If you've ever seen what looked to be like a hazy halo around the sun or the moon, but it didn't look like there were clouds, there may have been clouds. They may just have been cirrostratus clouds. Thicker ones can indicate approaching storms. So, watch out for that. All right, so let's talk about the middle clouds. These are composed mainly of water droplets with some ice crystals if it's cold enough, but that would be so because they're middle clouds. They're not quite high enough for the whole thing to be frozen. So remember that alto means middle height. So any cloud that has alto in the beginning of its name is going to be a middle height cloud. Altocumulus, those are gray puffy clouds that may form waves or bands across the sky. And altostratus clouds, remember stratus are the layer ones, altostratus would be a gray layer that often covers the entire sky. So if it's overcast, you may be looking at altostratus clouds. They're thicker, they're more gray than cirrostratus clouds. Those are the high up stratus clouds. The sun or moon may be visible as like a dim round disk. And altostratus clouds often form ahead of widespread storm systems. Okay, so we got the high clouds, we got the middle clouds. Next up, low clouds. So low clouds are usually composed of water droplets. They're not high enough. It's not cold enough for them to contain ice crystals or, if it's really cold weather, they may contain ice crystals, possibly even snow. So the kinds of low clouds are nimbostratus. The nimbo there means dark, right? Dark gray cloud layers associated with continuous rain or snow. The grayness of a thick cloud is just a shadow. It's not like the cloud is actually gray. It's just that it's really thick, and so the underside of it is dark. Not a lot of light is getting through. They're too thick for people to see the sun or the moon, and they don't rain really heavy, but they do rain a lot. The precipitation is light to moderate. It's not going to be heavy rain. All right, so stratocumulus. Remember, cumulus means like puffy and I can't remember the other word for puffy. Anyway, so stratocumulus. Those are low-level clouds that are characterized by large, dark, rounded masses, often in groups, lines, or waves. And stratus clouds would be a uniform gray cloud that often covers the whole sky. You can't like actually see individual clouds. It's just one huge flat cloud. It doesn't produce precipitation except for like occasional light mist or drizzle. So basically this is just like a really gross day. Kind of maybe almost rain all day and it's overcast. So yuck. Maybe produced when like a heavy fog lifts from the surface. So it's just high up fog. I mean, that's what fog is. It's a low down cloud. All right. One more low cloud. It's called cumulus. These would be puffy, low-level clouds that usually form as individual, domed, cottony masses with plenty of blue sky between clouds. They're common in fair weather. They may develop into thunderstorms. Those would be cumulonimbus. Later in the day, that would be like your classic summer afternoon thunderstorm. Though some may have more vertical development, growing upward due to convection. Those are the ones that are really, really nuts. In terms of like thunderstorms, the really tall, like, thunderheads. Okay, so since we're talking about thunderheads and clouds that can turn into thunderstorms, let's actually talk about that a sec. I named them a minute ago, cumulonimbus. Those are thunderstorm clouds. The bottom is dark because it's very tall, so there's a lot of sunlight being blocked. But from the outside, right, like from the side, if you can see it in the distance, it appears white or light gray. High upper level winds can often reshape the top of the cloud, forming like a flat anvil. Thus why it's called a thunderhead, okay? So just imagine you got a cloud that's rising up and then it reaches a region where there's a wind at a certain height and it kind of just shears the top off of it. It almost makes it look like a big anvil. So thunderhead is what we call those. Okay, so we got clouds. Now let's talk about precipitation. So precipitation is when the water that is suspended up in the air as microscopic droplets condense. They form droplets or some sort of ice crystal or something that's too heavy to be suspended in the air and they fall down. Different kinds of precipitation, like, various liquid and solid and semi-liquid and semi-solid versions. You know them: rain, snow, sleet, hail, and how they form depends on where they form a lot of the time and what the temperature is there. Much of the rain that falls actually forms at high altitudes, but snowflakes form directly from water vapor that never formed raindrops. Snow is not frozen rain. That is actually sleet. Sleet is frozen rain. Feels weird talking about all this winter stuff like on a really nice warm spring day, but when we're talking about frozen rain, that would be sleet, but freezing rain would be rain that falls and then freezes. So we got rain that condenses and precipitates at high altitudes. Snowflakes form instead of raindrops when the water freezes. Sleet is raindrops that freeze as they fall. And there is a particular kind of cold precipitation that we haven't discussed yet, and this one isn't even limited to winter. That would be hail. Hail forms in thunderstorms, not usually in winter. Hail is more of a summer thing. The way that works is thunderstorms are so violent with their wind that rain forms and falls, and then it gets blown back up to a high altitude where it's cold enough to freeze, and then it falls back down, and then it gets blown back up where it refreezes again. And so you get this like building up layer of frozen and refrozen raindrops, and depending on how strong those winds are, they can remain aloft and building for quite some time until they're like, described with various forms of fruit, pea-sized hail, walnut-sized hail, grapefruit-sized hail, watermelon-sized hail, just pumpkin? Boy, I hope not. Anyway, so that's what we've got as far as precipitation goes, let's talk about weather as you'd see it on a forecast. And this is where I need the Earth again. Oh, the Earth is getting a little deflated. I need to blow up the Earth again. There we go. Okay. This is where these markers are going to come in handy as I'm talking about the Earth and how it appears. So first thing that I want to define for you is an air mass. Not an air mattress, an air mass. An air mass is an extremely large body of air that has similar temperature and moisture characteristics throughout. A large mass may cover like a significant portion of a continent or an ocean. So like really it's just like I could have my whole hand, okay, maybe that's a little big, but like a large portion of this globe would be covered by an air mass. And it's just one big, collection of air that's all fairly similar in terms of its humidity and its temperature. They tend to resemble the region from which they come, which is called its source region. So let me point out a few and I will label them. First, we've got continental tropical. Continental tropical would be one that forms on a continent in a tropical region, and its abbreviation is lowercase c, capital T, and it's called continental tropical. On the other hand, if we come out here to, say, the Atlantic Ocean in the tropics, we have something called maritime tropical. So little m, capital T, we call that maritime tropical. Okay, so let's go kind of like to the opposite of that. Let's go up far north off the ocean to where it's very cold. Looks like I'll have a lot of space in Russia to write this. So if you are in a polar or near polar region and the air mass is coming from a continent, we would call that continental polar, and it's abbreviated lowercase c, capital P. So continental polar air masses will be cold and dry. But if we are talking around like an ocean region around the pole, even though it's cold, there will still, I still need blue, there will still be some moisture in it, and that is going to be called maritime polar. So let me write little m, big P, maritime polar. And the very, very coldest is going to be continental Arctic. So continental Arctic is going to be further north than this even. It's going to be the kind of thing that you get from like the top of Greenland, or maybe up here north in Canada. Also, you can barely see it down here in Antarctica. So I'm just going to write it down there on Antarctica. It's called continental Arctic, very cold and very dry. Little c, big A. So those are the names and types of air masses. Air masses are extremely large bodies of air that have similar temperatures and moistures throughout, and they resemble the area from which they come. Weather patterns are basically just interactions of air masses, okay? So air masses are going to form here, and then they're going to just get moved around by those global wind systems that we talked about before. So let's say we've got a maritime tropical air mass. It forms in the tropics over the Atlantic Ocean, and so it's very warm and it's very moist. But it gets caught up in these prevailing easterlies, so it blows west. Okay, so that means it's gonna, say, move over the Caribbean and maybe like into Mexico or to the southern United States. At that point, it's going to start to take on that region's characteristics. It's not going to remain very moist. It's going to start to lose its moisture as precipitation. And so you're going to end up with a lot of precipitation in this area that came from the Atlantic Ocean. Now, you are going to have, say, let's see, where'd I put another one? Okay, you're going to have similar but opposite if you've got like a continental air mass, whether it's continental tropical or continental polar, that well, let's see. Let's go from here. Actually, this isn't a very good example because it's near the horse latitudes. So maybe we should go with one like here. Here we would have a continental polar air mass, and this continental polar air mass would be moving with prevailing westerlies, which means as it moves eastward, it's going to end up over the Atlantic Ocean, and it'll pick up some moisture from there. Okay, well, speaking of maritime tropical and continental polar, let me actually write a continental polar on here, because this is what matters for us here in the United States and in the northern hemisphere and the western hemisphere. We got a maritime tropical and a continental polar, and they surround us. We are surrounded by a maritime tropical and a continental polar air mass, and that actually determines pretty much all of the weather that we have. But there's another name for all of the weather. We could just call that climate. So it's responsible for our climate on the near east coast of the United States. So let's talk about fronts now. I mentioned fronts a little earlier, but I didn't define them, so let's do that now. A front is a narrow boundary or zone where two distinct air masses collide. So if this maritime tropical and continental polar air masses meet, they form a front. Since we've got right here in the middle where they will probably meet a lot, that's where you have a lot of heavy weather. And if you've ever heard of Tornado Alley, it's this little spot here in the southeastern United States where there are a lot of tornadoes. That's why there's so many tornadoes there. It's because it's right where this cool, dry air and this warm, moist air meet most often. Okay, so let's talk about how these two air masses will interact with each other. So let me go ahead and I'm gonna regret this. All right, I can't avoid it. So I'm gonna label my hands. So I'm gonna make this be a I'm gonna make sure I don't screw it up. Continental polar air mass. Ugh, the things I do. And this one is going to be a got to write upside down with my left hand. Wish me luck. Maritime tropical. Hey, I didn't do bad. All right. There we go. So I got my maritime tropical air mass and my continental polar air mass. I really hope I don't mix these up. So a cold front happens when a cold air mass is moving to displace a warm air mass. So since the cold air is more dense, it ends up wedging under the warm air, and so it pushes this warm air up into higher latitudes. Okay, so it's like kind of goes under and pushes it up. Once the warm air gets pushed up to a higher latitude, then it goes up to its the altitude where the dew point is, so it ends up cooling down quickly because it's being forced up. It cools down, its water vapor condenses, and it leads to precipitation. So a cold front is one that's intense, it moves rapidly, and it produces a lot of rain because this cold air is just forcing that warm, moist air upwards to where the water can condense, and then this precipitates. And so that's what a cold front is. They often move really quickly. They produce strong winds and heavy rain, even thunderstorms and snow. Most of the precipitation occurs near or behind the front. So the front is just where they meet. The front would be like the right here. It's the boundary between the warm and the cold air mass. And so since the warm air mass now cooling down, is the source of the precipitation. It's going to be producing its precipitation like behind the front because the front has moved on. It's almost like a reverse fault, if you remember that. So yeah, it should be pretty obvious in a picture. The temperatures may drop dramatically because cold, continental polar air is coming in to displace warm air that was there. So you're going to have a sharp temperature drop, strong winds. All of a sudden, the weather just turned totally nasty. And this is symbolized on a weather map with a blue line with teeth or flags pointing in the direction that the front is moving. All right, so that's a cold front. Let's talk about a warm front. That would be the opposite kind. A warm front is where the warm air mass is advancing against the mass of colder air. So it typically moves more slowly, so there's going to be less friction, so there's not going to be as much intensity. The friction is what causes lightning, so you're not going to have like a thunderstorm. It's going to be a much more gradual slope as it runs over a cold air mass. Okay, so it's going to produce extensive areas of cloudiness and widespread light precipitation that occurs ahead of the front. Okay, so basically the warm air is going to come in and kind of just glide over the cold air. So it's going to be much more gradual and gentle. It's not like it was forced up to cool down quickly. It rose up smoothly so it cools gradually, and it just makes this big cloud that spreads out. You're going to end up with stratus clouds there, and it's going to be overcast and just kind of rainy a little bit for a really long time. Warm fronts tend to not cause intense rainstorms or thunderstorms. They cause those all day, I can't go outside, like overcast, rainy weather. So typically, I don't know, it's just a preference. I don't like warm fronts, even though they make it warmer afterwards, which can be nice depending on what month it is. It kind of just makes the weather gross. It's symbolized as a red line with bumps pointing in the direction that the front is moving. Okay, so what about a stationary front? We had a cold front, and then we had a warm front. What about a stationary front? That's where there's little horizontal movement along a boundary between warm and cold air masses. So the weather is similar to that along a warm front. It's just like, widespread cloudiness and light precipitation, but it's not moving. If it does begin to move, it's a weak front. So if it moves this way, it's a weak cold front. If it moves this way, it's a weak warm front. And it's symbolized as like a combination of the symbols for warm and cold fronts. Okay, there's one more kind of front. It's called an occluded front. It is actually a cold front that has caught up to a warm front. I'm not going to be able to do that with my hands because I can only make one front at a time, but cold fronts move faster than warm fronts, so you can actually have a cold front catch up to a warm front. When it catches up, the warm air mass is squeezed between two cold air masses and lifted up. I should have said squeezed instead of like squeezed. Squeezed between two cold air masses and lifted up, and it's symbolized as a purple line with teeth and bumps. So the symbols for a stationary front and occluded front are just two different ways of mixing the symbols for cold front and warm front. So you should see those on weather maps. Next time you see a weather forecast, if you see those symbols, you should be like, I know what that is, right? So weather maps are going to see, we're so used to certain kinds of weather maps because we get our weather from like smartphone apps. We get them from websites. I haven't watched a weather prediction on the news for a long time, actually. But there's a lot of symbols that are worked into weather maps to kind of communicate a lot of information. So, you're going to have like different things like low pressure and high pressure that are indicated on a map. And that's useful because low pressure systems are usually associated with storms, high pressure with fair skies. That's like how you can use just like a barometer to try and estimate the weather. So the symbols, I feel like it's going to be kind of difficult for me to just describe them because I'm talking about what things look like, and I'm also trying to condense this. So I think I'm going to leave the details of what weather maps look like kind of off for now. Okay, so here's what I can leave you with in terms of, like, just something to sum this up and make this final. One, I need to wash my hands. But two, I want you to be able to notice this about your local weather, okay? So this is about the weather where we live. And obviously we don't live in the exact same place, but we live in the same region dominated by the same air movements, specifically the prevailing westerlies between 30 and 60 degrees latitude. And especially for us, because we live on the east coast of a continent, so our continental polar wind is coming from the west, and our maritime tropical wind is coming from the east. So if you have never noticed this before, I hope that you will. Spend some time outside looking at clouds and watch what direction they move. If you're too impatient, I guess you can just set up a time-lapse video and watch that, but come on, look at some clouds. Anyway, the point is, they move from west to east in our sky, typically. And that means they'd be moving from the sun set direction to the sunrise direction. So if you've never noticed that before, hopefully you will. And this actually ties into something that you can use, maybe you've heard of before, to kind of make, amateur predictions of the weather. Have you ever heard this expression, red sky in the morning, sailor's warning, red sky at night, sailor's delight? Have you ever heard that before? That's a really, it's an old expression. It's actually so ancient, it's kind of referred to even in the Bible. That's how old it is. And it kind of makes sense even there because the Middle East is still in those latitudes. So what does this expression mean? How does it work? So it works like this. Red sky in the morning. Red sky in the morning means that the sunrise is illuminating clouds. When the sky is clear, the sunrise looks, a little tinged red and orange on the east side, but mostly the sky just turns blue right away. It's only red if there are clouds in the west for the sunrise to illuminate. If there are clouds to the west, and you live in a place where there's a prevailing westerly, that means those clouds are approaching. In other words, you've got clouds coming probably from a cold front because it's continental polar air pushing maritime tropical air out of the way. That's what those clouds are from. It's westward clouds moving eastward, so you're going to have clouds over you soon. That's the meaning of red sky in the morning, sailor's warning. What about red sky at night, sailor's delight? Well, red sky at night means, if the sky were clear during a sunset, the sky would just go dark. However, if there are clouds in the east when the sun is setting in the west, then they will be illuminated with the sunset. They will be red. It's sailor's delight because if your clouds are in the east, they've already passed you, and you don't have to worry about any bad weather from those clouds. Okay. Anyway, that is, it's a lot to cram into a little bit of time, but I'm going to be honest. I really want to do space because this remote learning experience, it's been great. It's been awesome. It's been wonderful, and I've enjoyed every single second of it. So I want to put this topic away, and I want to do something that's enjoyable and interesting and unusual for the rest of the year. We can just spend 2 weeks on space I've got a plan for it. Obviously, there's a lot to cover. However, space is one of those things that everybody loves. It's like dinosaurs, right? And if there is a particular topic that you'd like me to cover when we're doing space, please let me know earlier, better than later, because I might be able to actually work it into what I was doing anyway. Mostly I'm going to be covering just our solar system. But, like, hey, we got a whole universe of stuff to study. It's not a whole astronomy class, but, it's space. Come on, you got questions about space and stars and black holes and nonsense. So what do you want to know about? Let me know. I'll try and work it in because, I'm not doing this for me, obviously, because, look at my hair right now. But I want this to be enjoyable and memorable for you. Also, it's like remote education. I don't know, maybe we should have a class at night or something. I don't know. Anyway, yeah, I'm going to go inside now. Bye-bye.